So solid state NMR decoupling. So the context, it's 36 slides. I was saying something. Okay. The context that we'll start with is that we're detecting carbon. And I'm going to build it up from what I think are the easy cases up to the harder cases. And hopefully the easy cases will reinforce your skills today, your intuition. So let's say you add a nitrogen connected to that carbon, which will be the case if it's a backbone carbon or many of the carbons in nucleic acids. And let's say that you're looking at this carbon that you're detecting, if you're looking at it in an indirect dimension. Okay? And that nitrogen might have a variety of couplings. We'll start to unpack that maybe on the next slide. We're not saying how it's coupled or what that coupling looks like, but I'm just going to say phenomenal logic. MAS alone doesn't generally remove the full effects of a direct bond. So we're going to have to do something with impulses. Also, simply flipping the nitrogen halfway through an indirect evolution period usually does suffice if you're also doing magic angle spinning. So this is just like procedures, protocols, what we do. Well, let's talk about our understanding of why that would be true, like why that's enough and we don't need to do anymore. So when we think about this problem, some simplifications. We're going to be ignoring all the relaxation during the time course. Something's happening, but we're just figuring that that is going to operate independently enough of the coupling that we can do the theory without explicitly taking it into account. For the moment, we're also going to ignore chemical shielding and anisotropy. And we're going to assume that the chemical shift is on resonance. So we're just focusing in on this coupling, what it takes to get rid of it. And when this is the part that, because I did it sort of hastily between yesterday, mostly in the wee hours between yesterday and today. I think it's consistent now that throughout, when I talk about carbon-13, I'll call it S. And the thing I'm trying to decouple from it, if it has a name, it will be I. I hope it's consistent. And the initial state that I'm thinking about will be SX. So I've already gotten it into the XY plane somehow. And I'll have Hamiltonians that might be a J coupling between the detect carbon-13 and the coupled N15, or a dipole, HT. And they are going to be evolving during what we're thinking of as a pre-precession period. And there'll be magic angle spinning going on, and maybe a bias. So that's all we're doing. It's the preliminaries. So let's say we're just talking about the J coupling. So that's very solution-like. And we're familiar with this Hamiltonian. Does that look right to you? Okay. And so therefore, if I say at time 0 it's Fx, at a later time t, it should be Fx times cos 5 jt, and then this funny antiphase coherence times sine pi jt. Everybody good with that? Now, I could use a pi pulse someplace. I could either apply it on I or on S. I could evolve for another time t, and typically this is a problem that you guys could do at this point. Question? So, for example, I approached it like this, and I'm not going to do everything in this problem, but just off the basic sketch. But I would think that this is something that I don't need to spend a lot of time on, because if I gave it to you as a problem, you probably will have already done it. Let's say I choose to apply that 180 on the spin of interest. It would reverse the direction of the magnetization. So if it's an X pulse, it would only affect this piece, not this one. And then I'd evolve for another time. And so after that second time t, so the signal at 2t, I get all of this, because from this piece, I then grow these two terms. And from this piece, I then grow these two terms. And you notice that if I add all that up, these two cancel, and these two add up to one constant. Okay, so that's an echo. That's an echo. We can do a pulse like that, and we can have what I would call an echo, which you could also say I refocused J and mean the same thing, and I could also say I decoupled. So this is one example of the way we usually word decouple, is that if the coupling evolved, that happened, I just made it go away by the time I refocused. So that was the single pulse on S. And by the way, it would also refocus the chemical shift if we hadn't been on resonance that's on echo, right? By a chemical shift, everybody good with that? You stop. Don't be embarrassed if you forgot something or it don't make any sense. You stop. So if you had a chemical shift, that would be an echo sequence to refocus your chemical shift. So maybe you didn't want to do that. Depends on what you're doing. If you didn't want to do that, maybe you should have pulsed opposite. And that's the more typical protocol that I'm measuring carbon. I want the nitrogen to not show up as being a coupling, so I put a little pi pulse in the nitrogen. You see this all the time in our pulse. Pulse on both, as you might realize already, you will refocus both chemical shifts, but you will not refocus J because you're basically changing the sign of J twice. It's not going to refocus J. All right, so those are things you've seen before because they're very solution-like. Now, I didn't have to grind that out as being, let's follow my magnetization around. I could have used what we developed earlier in the course as toggling frame or interaction frame when I was talking about that average Hamiltonian theory. Remember this? So instead of saying I'm flipping magnetization around, in that picture, we say I'm flipping my Hamiltonian around. So the Hamiltonian initially is this, but after the pi pulse, it becomes this. The Hamiltonian itself changes. And if I put that pi pulse right in the middle of a period, I say I spend half the time with this Hamiltonian and half the time with this Hamiltonian, like having zero Hamiltonian. That's magic. So that's the first term in what we're calling the Magnus expansion, giving you the first order effective Hamiltonian, average to Hamiltonian, instead of grinding out what happens to the magnetization. Everybody still with me? This is all like refresh, review and refresh. Now, what about when you're actually wanting to talk about the direct detect dimension? Everything I just said is only good for an indirect dimension, where you put a pi pulse in the middle of it. That doesn't work for the direct. That doesn't even make sense. The direct, if we did it that way, we would be seeing these J couplings come and go on our FID. It would be very ugly. So what do we do in the direct detect dimension? Well, you could actually irradiate constantly, and I'm going to have an example of that later, so I'm not going to do that right now. Did you already in this class study some of the pulse sequences for the direct detect dimension, such as waltz? So you're detecting carbon and you're doing something on nitrogen, but it's something more complicated than a CLU. Did you already talk about this? No. Well, I didn't really develop something about this. I should have. I like this pulse sequence very much, even though it's the solution. She says in her patronizing way. So this is a A.J. Sharko when he was in Oxford, I think. And it's a low power way of doing a really good job of decoupling the J-coupled spins. So you're going to irradiate, in this case, in my example, the nitrogen while you're detecting the carbon. And it's a composite pulse that does a better job than CW. We can go back and talk about it. I never really did prepare this. I thought it was just going to be a flashback from another lecture. Maybe we'll talk about it before the class actually ends. But now let's turn to something that is much more solid, like that I did include in the deck, which is what if this N15 is actually dipole couple? This is a sol, right? So it's not just a J couple, it's also a dipole couple. And what would the difference be? How would the dipole coupling differ from the J coupling? Or how would it be the same? It's in the same form, ICSC, right? Or what did you just say? Oh, we could have an I.S if it were homonuclear, but as it's heteronuclear, it's also truncated for most applications in solids. So those other raising and lowering operators or X and Y terms, mostly they go away because of the difference in the general magnetic ratio, the fact that it'll be like a secular approximation. So we're going to have a similar Hamiltonian, ICSC type Hamiltonian in the first instance. When we put those terms back in, it would be homonuclear, okay? So it takes the same form because it's truncated, because it's heteronuclear. But the key difference is that the dipole coupling is orientation dependent and much larger. So how does that change matters? It's orientation dependent. So it has this prefactor that depends on the gyromagnetic ratios and the distance on a null constant. And then a geometric factor that we spend a lot of time talking about this. So the second Legendre polynomial. But if we're doing magic angle spinning, that second Legendre polynomial becomes time dependent. So the magic angle spinning pulse refocuses or decouples it, because we spent some time deriving this, that the instantaneous frequency as an offset from whatever the frame center is, the isotropic shift or whatever, that frequency is sinusoidally varying, so its time averages you. So for the dipole coupling, even though it's larger and more complicated, we don't need to do anything with the pulses. It's already averaged to itself. So that is different than J. The J, you have to do something, but it isn't even that big, so sometimes we forget to do anything in solids if our lines are broad. But in a good favorable case with a nice sample, we should put that kind of pulse. But the dipole, so supposedly we don't have to do anything. And in fact, if we do something, we're going to have to be careful. We have to be careful with additional pi pulses, because as it's already decoupled from the magic angle spinning, we saw examples earlier in the term where adding another pi pulse could recouple, could make it come back. Do you remember that? Yeah, so be careful if you need to add this pi pulse. You place just the one pulse on a rotor echo in the middle of a long period. You're not going to recouple. The recoupling sequence is always going to be doing something every single rotor cycle or multiple times a rotor cycle. So you could do this J decoupling with a pi pulse, and you can simulate it, and you're really not going to create a problem with your dipole coupling. Strictly speaking, you should put it right on a rotor echo, because at the end of each rotor echo, you finish the cycle, and now you start fresh again. But in practice, even if you are not synchronous perfectly, you're good. The recoupling sets in when you put multiple. Now, here's why it's not all reviewed. So we've talked about a few things that we saw before, and I'm just refreshing your memory and carefully defining what I mean by decoupling, but we have another case that's got some ugly features that we never did talk about before. Let's say you're doing carbon detect, you're doing MAS experiment on your nucleic acids, and you have some proton-proton couplings and some carbon-proton couplings, and both of them are quite strong. And we were in some of the sugars, all of the amino or most of the amino acids can have geminal pairs of protons, and those are only about 1.7 angstroms away from each other, right? And they have couplings that are like 20 and 30 kilohertz. And that's pretty strong, you know? I mean, that's stronger than most of the other things in the problem, except for the strongest pulses or the fastest spinning that we have available in the lab. Most of the things we do, that coupling is going to exceed. So they will evolve significantly during one individual MAS period if you're using a normal rotor, not an alternator. You start out with the coupling not being encoded in any way in the spin state, it's just IX. And by the time the rotor period finishes, you've really fanned out to in one rotor period, you fan out to an anaphase coherence or more. And I say or more because every proton in your sample has multiple neighbors. So there is no proton in a typical biopolymer, unless you do something exotic with your isotopes, where it's just looking at the one proton neighbor. There's no carbon, which only has one proton neighbor. You step out into 2 angstroms, and you're going to find a whole network of protons. And so a lot of evolution can proceed even in one or a few MAS periods. So all of this makes it very crucial to remove the effects of proton couplings in the direct and the indirect nature periods. And moderate MAS or high pulse is not going to cut it. Does that make sense? The strength of the couplings and the fact that it's a whole network. And this isn't comparable, no matter what you pick for your isotopes, to what will happen for the carbon or the nitrogen. They might be in a network also, but it's just that much weaker because of the general magnetic ratio and the typical distances and the topologies. So that just the MAS that we're capable of doing with a little high pulse is more than enough. So it's a unique problem to the protons. If you had a little network of fluorine, but we don't. We don't have these perfluorinated things very often in our. Now, what I'm showing you for the graphics for the next few slides comes from a nice review article from a leading person for the theory of solid state NMR, Matthias Ernst. I believe is no relation to Ernst. And it's actually his habilitation thesis. So this review article and his thesis have a lot of text in common. And now we're talking about the problem of you're detecting a carbon and you have a lot of protons in the sample that are coupled to each other and to the carbons. And you have a dipole Hamiltonian, the heteronuclear dipole Hamiltonian. What we've been doing traditionally in the field, like from the 50s up till sometime in the 90s, I think, you just turn on a really strong irradiation on the proton channel while you're detecting the carbon, whether it's indirect or direct. Having that much irradiation on the proton channel and having your receiver hooked up at the same time normally should give a person a pause. But the RF power, because it's a double tuned coil, right? You have the one coil, or at least just have one coil, and then you might be measuring proton with one variable capacitor, and carbon 13 could be on the other side or the same side, often it's on the other side with another variable capacitor. So if I come in on the proton side and I put a whole bunch of RF, that's directly on the same coil where I'm going to hook up a receiver. We use filters on both channels so that the proton irradiation is not giving you anything at carbon, and the carbon receiver is not listening to anything at the proton frequency. And those filters give you good isolation between the two operations so you can turn on many watts of proton irradiation at the same time that you're listening to a microvolt kind of signal on the same one. That's called good isolation. So when we do that, what happens? Here's magic angle spinning for just a little dipeptide, and the spinning is 28 kilohertz, so that's kind of mid-range for modern equipment. And then this is if you turn on CW decoupling, which doesn't say here, but I think was about 100 kilohertz. You're going from unusable poor resolution, especially at the phenylalanine resonances here of the carbon spectrum. And the alphas are very much affected by the rigid attached protons. And particularly on the CH2 residues. And then all of a sudden they become usable with the CW. But this was the practice. This is what people do. And what's the thinking behind it? Like, how is that working? The cartoon in the last slide, Matthias Ernst was trying to convey that since you're doing two things at once, you're doing the CWRF and you're doing spinning, that you probably want to think about them in a hierarchical fashion. One of them is stronger than the other. If in this case, the RF is very strong, you think about what it's going to average as if there were no rotor. And then once you get the average of all of that, then you say, take that average and now predict what MAS would do. That's what this figure was meant to convey in this paper. So think about a quasi-static regime. If we're going to use high power decoupling and lower frequency spinning, pretend the spinning, it doesn't matter. Go into the interaction frame or toggling frame where you're following the RF, thinking about what it does to your dipole coupling. Here's your dipole coupling, truncated dipole coupling. And what I'm going to do is irradiate at I, or carbon is S, then I will become this. So I'm rotating that piece of the Hamiltonian around the RF, going in a frame where I don't see the RF, where I follow the RF. And so I get a time-dependent dipole coupling, which has two geometric distinct operators, and each one of them sinusoidally varied. You say, what's the time average of that dipole coupling? What would you say? Is zero, and it's a zero time average. So the first term of the Magnus expansion is the simple time average, and its answer is zero. That's the idea. This picture doesn't explain everything. It's really nice. It uses tools that we've developed. It's very intuitive, but it actually doesn't explain all the spectroscopy that is out there. So we know that probably a stronger RF will be better. High power means that the cycle time for averaging becomes short, and then there would be less evolution of the coupling, and maybe you could come closer to pretending that every carbon only has one proton. Maybe you don't have enough time during one CW irradiation cycle to get out to the more remote spin. So that's the hope. Again, a very intuitive physical picture without any math to go with it. And in practice, historically, we'd say if you've got a probe that you can't turn it up any higher than 70 kilohertz, well, you're not going to get good spin. We like to have most of our probes here run with 90 to 100 kilohertz. If you want to go above about 75, you should have some documentation on that probe and a previous experienced user. And if it's here at NYSTC, that they're at Kilo. If you want to turn it up even tonight, you need permission, let's put it that way, until you're super experienced, you talk. But that's a really narrow window. I'm saying 90 is, yeah, check, I don't know. And then 70 is almost not good enough. So you get the sense that we're barely achieving these experiments, right? But I said, this picture doesn't explain everything. Let me give you some really nice examples out of the same review article from T3. So when it's beneficial, it improves slowly with omega, and then we tap out because we're pushing the probe too hard. But sometimes, even when we're near the top, we see trends that don't make any sense. Let's start with this one. This is alanine with a C13 enrichment. on the alpha site or tube site. And for some reason, the CW decoupling is 100 kilohertz, just chosen to be that. And then you vary the spinning frequency. And you can see that the spectra look a lot better if you spin slow. See that? Take a minute. I don't mean to rush you guys. I don't need extra time today, so shouldn't hesitate to stop me or ask me to repeat. These are simulations. There's more to it in the paper where he's actually exploring an underlying model or hypothesis for what's going on that has to do with spin diffusion. So the simulations I'm not really going to explain for right now, but you can see the phenomenologically that has nothing to do with what I just explored. So there's something else going on. Over here, this is an N15 spectrum of trimethyl ammonium fluoride. And initially, no CW, just EMS. Got a J coupling of about 100 hertz apparently, and MAS is about 30 kilohertz. And you start turning on RF, strong RF, and it would appear it's made matter force. Then you decide to go get a stronger magnet because you don't understand what's going on, and that makes things even worse. And there's a good explanation for all of this. So clearly our little simple explanation for CW decoupling is something. It's something, and it's not entirely wrong, but it's not adequate. And this is the same compound, trimethyl ammonium fluoride, as a function of proton decoupling power, where other things are held constant. And yeah, it's slowly getting better. It's not asymptotic to a beautiful singlet. So we need to understand this a little bit better. They're strange phenomena. Yeah, go ahead. How is it different from what?
So if you're close to you're saying like that's sleep.
It is part of what's going on. We're gonna go right to that. Okay, so I think here, higher omega-1 is better, but we have to consider homonuclear recombination. That means that be a purpose. If omega-1 is equal to omega-R, that was one of the homonuclear recombinant conditions we talked about a month ago. And there's another one where omega-1 is half omega-R. There are other phenomena where omega-1 is 2 omega-R. You remember I referred to a minefield of conditions. And the problem is not just that there are conditions. The problem is that the matching conditions need to be missed by a wide margin. You don't want to be slightly off of them. And the way to think about that is that you need to be off of them by an amount comparable to whatever the coupling is you're working. If that's CSA or if that's dipole, here we're talking about dipole coupling. The dipole coupling is 20 or 30 kilohertz. I need to be off of these matching conditions by 20 or 30 kilohertz. Okay. So that's how I'm just barely squeaking by at 70 kilohertz. Now all of a sudden it makes sense. I'm spinning at 20 or 30 kilohertz. I need to be up at 90. And actually my target might be something more like the order of magnitude of 300 to make sure that I really don't see these effects anymore, because they only decrease like 1 over omega R. They decrease very slowly. But in practice, we go up to the arcing limit and then come down so that advanced users like with a big mess, and then limits our approach to about 90. Another caveat that many people don't learn early enough in their work, but some probes have a huge electric field, not just a magnetic field, but an electric field in that coil. That heats your sample. It's a dielectric heating not too different from a microwave oven. And it's significant. It's like 30 or 50 degrees C. You could take a warm sample right to boil with an hour. We have other probes that are just, the coil geometry is different, and they are so-called E-free. They are almost E-free, okay, and they can be used to do high power decoupling without very much heating up the sample at all. Generally speaking, because of the geometry and we can get into this more if you guys want to talk more about our work. Generally speaking, when you have the geometry for E3, actually, you get more limitations on the power handling because they're just coil geometries that are more prone to parking. So, it's not a panacea, but you're being more careful with your sample. So, you select hardware to do your experiment on. That should be one of your questions. What's the maximum power the probe can take? What kind of sample holders do I need? How much protein do I need? But does this probe eat my sample? Needs to be on your checklist of questions when you're planning. Okay, so we're talking about recoupling conditions. This is basically what you brought up with the slide. If you remember this, we were talking about the Hartman-Hahn, and I had this like laundry list of interactions in the rotating frame, and then I transformed them for you into this so-called doubly toggling frame. Doubly because we were going to have an RF pulse on both channels. So the decoupling topic is actually the same thing, but it's slightly easier because we don't have the RF on both sides at the same time. We only have the RF on one channel. So we're only rotating around I, not S. So I changed the table up just a little bit to accommodate that. So, for example, there is no S spin lock field. The IS heteronuclear interaction has SV remaining normal and just rotating IZ. The I interaction is the same as on the last table that we saw before. Chemical shift offset for S, nothing happens to it. Chemical shift offset for I, same as the last table. That makes sense, right? We've seen this before, it's just simplified. But I'm going to suggest that back then, I left out the CFA. I said this is an intense problem for your first introduction to average chemical motion. Leave out the CFA for the first time. I need to put it back in for this problem. So in this row, in the last slide, I just had this. Now I have this plus this. Isotropic shift is an IV type operator. CFA is also an IV type operator, but it has this offset that's anisotropic, and it's a function of time, and it's on the next slide, it's taken just from what we derived together. Right? So the delta omega is relative to the isotropic shift, and it's all of this stuff for chemical shift. Could be that you want to set eta equals to 0, and then you can simplify it massively, but in a general case, this is the worst it could be. So that is what I mean here by delta omega up to the thing we derive. And I'm going to put that in for both I and S. And again, because I'm not irradiating S so far in this problem, I don't need to transform it. This one gets transformed, both pieces and out this. I've assumed in these expressions that the pulse is strong and really covers the whole spectrum, covers the whole CSA. So in terms of some of those terms on that whole big laundry list, some of them are such that first order Hamiltonian theory would be enough. First order is enough if everything commutes with each other. So when we start calculating things like that, they're all 0. So if I have a laundry list of interactions, if they all commute, no matter which moment in the rotor I'm talking about, they commute with themselves at a later time, they commute with the other terms, all commuting, well, we don't need all this. We can just do the time average, just take the break. That, for what I've laid out, is the case if I only look at the S subspace. If I just look at the terms that depend on the S operator, there's only one kind of S operator, that's SV. I didn't generate anything else, I have no RF. But what we're worried about is an IS coupling. So now we have to say what happens inside the isotope. And we're interested in it because of this coupling. And already it doesn't compute with itself at many times. At some moments of the rotor, I'll have more IZ. At other moments in time or positions of the rotor, I'll have more. I don't know why that doesn't. Just it's itself. It's already is. However, what about its own homonuclear coupling? Is this bigness? Where we do put those things back if we're talking about this because it's very similar mechanical shift. None of that. You have everything from the dipolar alphabet and every geometric, every raising, lowering operator, whatnot. And there's another term, which is the CSA and the isotropic shift. So the isotropic shift, we could have just said, well, just be on resonance, want it to go away. But the CSA, there's no magic to make it go away. It is there, delta is big, and it has a Z and a Y component. So we have a big mess on the proton channel. We have 3 terms, and all 3 of them have complexity in the toggling free. So we have to keep these higher order terms. And that's our best understanding as to why our little picture of how CW decoupling is going to make everything good is staying to work. You could recouple certain interactions. And in any event, you should have never stopped at the rotor. That was never true. One thing that's gotten a lot of attention in the literature from within those problems is the interaction between the proton CSA and the HX coupling. That particular term, that particular cross term. During RF irradiation, the homonuclear proton couplings are also a known issue. So experimentally, I mean, in a simulation, and we didn't really talk a lot about simulations this term. Usually there's a little bit more about that, but there are a lot of simulation packages that are pretty user-friendly that work really well for solution or solid. That I would mention Simpson by name. It's a easy access, really good documentation, and the people who developed it are responsive. And they also gave a lot of like classic beginners examples that you can just play with by yourself. So I really can't say enough good about it. It does not and makes no intention of creating dynamics. So we never have dynamics in it. For that reason, in my lab, we tend to have some use of spinach, which is a major leap in the complexity and the activation barrier for getting going. And it helps a lot if you use MATLAB or for something, because that's what it's based on. And then there's another program, but it's not open source, which is from Mikhail Short, and it's called Spin Evolution. And he added at one point at our request some dynamics in it, and it covered a lot of things. It's super fast. So depends on what you want to do, which of those is your best choice. But in any event, you can use tools like that to get a lot of insight as to how much these 2 problems are really contributing for a concrete case. So you put together this spin system that's for your molecule of interest, and you can put in realistic CSA, and they both are serious contradictions. You can also do experiments. I mean, you can't make everything you want to make, but you can deuterate to make some of the protons go away. And you can change the applied field to make the CSA more or less work. So from things like that, we know that both of these terms are. Now, what happens if you have a cross term, like a product of 2 terms, each of which is a second Legendre polynomial in space, and now you're multiplying, you're not adding them. We're not going to get another second Legendre polynomial only. Just think about it, that polynomial is like piece of algebra you can write out, depending on the square of cosine of theta. And you multiply two of those, you're gonna get some other things, you're gonna get higher order terms, and you're gonna get zero order terms. Do you remember, Taylor and I were talking about that with respect to the quadrant, that we talk like PT cos theta is the only algebra we need for NMR, but that's not true. So when you have cross terms, you can get another shift that is not an isotropic shift, but it's a shift in your spectrum. And it comes from this cross term, but you can also get things that depend on the fourth power in angle and trigonometric functions of angle, and those don't spin out. So they also are going to behave peculiarly with CW decoupling in spin space. So spatially and in spin space, they're complicated. How big are the cross terms? In general, when you do that Magnus expansion, you can see that, let me just go back to that slide for a second, that you always, for each new term, you are going to entertain the product of two couplings. But then you integrate over one cycle, and that has the effect of saying, multiply these two couplings and then divide by the RX term. Basically, that's the way that plays out. So if I say my RF strength is 100 kilohertz, and I say each of my couplings is 40 kilohertz, each successive term is smaller, not hatched. So the cross terms, you might be thinking there's going to be a tiny little 1%. That is not true. They're smaller by the ratio of the CSA as to a ratio to the RF. So if you have a big CSA, the RF might not be that much bigger. So it doesn't necessarily converge that fast. Okay, so just looking at it a little bit like recent history, traditionally high power CW decoupling was very typical. They may, I don't know, we're starting in the 60s, I don't know exactly, and requires significant stress sample probe and amplifiers, does not fully remove the effects of the protons, and benefit increases only slowly with increasing omega R or omega 1. And like we say, you're going to get these cross terms. So improved sequences. For sure, we know they're out there, and there's some really cool examples from the older literature. Some are so-called window sequences. That means that what you want to do is suppress the proton couplings, but also measure them. So you come in on certain moments when you turn the pulsing on, you take a data point, and then you go back, pulse, and then you take a data point. Window sequences, and sometimes called stroboscopic observation by analogy with optical effects. So you're going to have detection on eye, decoupling on eye, measurement on eye. Sometimes this is for measuring those very heteronuclear dipole couplings we were trying to get rid of. Sometimes you can try and measure chemical window. And a good example of that that's historically kind of very special is Wahoo. Did you see that before? I'll show it to you very slowly. This will be the first thing I taught because it's a beautiful example of average Hamiltonian theory. But then I began to realize that students were feeling like I was teaching them things from Paleolithic period. So I stopped teaching this. But it's beautiful. So it's a group of 4 90-degree pulses, and average Hamiltonian, it's 0 to the first order. But there are improved variants where you do something about second order terms as well. So what's Wahoo-ha and why is it called something silly like this? This is John Waugh, MIT, at the beginning of rational development pulse sequences using average Hamiltonian theory. Simplest multi-pulse sequence for homonuclear decoupling. Ha here is this Haberlin who went on to do many wonderful things in NMR as well. It consists of 4 90-degree pulses and some short delays, and you can come in and detect on these delays. So that's the 4 pulse element, each one of these orange squares. And this was some of the early days of detecting protons with magnets that we would consider to be low field nowadays. And this particular layout of the graphics, they all came from different places, but it's Jeremy Tittman's course. He put this together this way. I thought it was nice. And basically, you can think about it in the toggling frame. It's the original example of what we do in the toggling frame, where you have this whole Hamiltonian for the dipole coupling, because it's two protons. And every time you hit it with a 90, you have to rotate that Hamiltonian appropriately. So you get these different expressions for the different times. And was arranged this so that it would all add up to what they wanted it to add up to, which was keep part of the chemical shift, but not all of it. You'd like to have all of it, but nobody knows how to do that. And you keep none, the first order of the homonucleotide coupling. So that was their design principle, and they achieved it. And you get what you call a scaling factor on the chemical shift. So which fraction of the chemical shift is still there is called the scaling factor. So if you actually do these experiments, you'll end up with chemical shifts that are overall compressed. They are pretty well resolved anyway. And then this is the basic building block, and then you can do super cycles to get rid of some known artifacts as well. Second order terms, offset tolerance, Smith set tolerance, V1 homogeneity tolerance. Phase transients refers to the old days of the amplifiers. You asked it to do a high power pulse, it could always have a big hiccup at the beginning and a little hiccup at the end. And we modified pulse sequences back then so that they wouldn't care about the hiccups. So when people went to fix this up better, often it wasn't to go to the second term in the averaging, even though it's a big term. Many times it was to go after these hardware imperfections that may or may not still exist today. So as you develop past this basic building block, you should always stop and say, the thing that they were trying to fix is it even relevant? Okay, another method, so-called Lee Goldberg, simpler, more elegant in some ways, is that you do the CW decoupling at a frequency offset so that the effective field sits at some angle, and you arrange that that can be the magic angle. And so you're doing in spin space what we usually do with the rotor rule, and it achieves much the same thing. Does that make sense? It's called the Lee Goldberg condition. So you turn off the CW pretty high, but you put it off resonance by a number you calculate, so that all the spins are basically doing magic angle spinning in spin sense. And it really works pretty well. You can get some nice proton spectra. Again, you'll have a scaling factor. You will not get a normal chemical shift scale. And there are ways to elaborate it to get rid of more artifacts, including something described in this paper by Tony Bialetti and Andrew Colbert from a long time ago. Okay. So those are some of the things that people thought about. Honestly, that would be in times that the computer programs for simulating were pretty simple. So they were using their brain and paper and pencil to come up with these very clever ways. Now, if you cut to the next generation of pulse sequences, there's one that still has impact today that I'm going to mention. So those that I just mentioned are more conceptual, they're beautiful, but how much are you going to use them? I don't know. Today, you go get a solid state NMR pulse sequence, and you might find that instead of CW decoupling, you're going to be using something called TPPM, two pulse phase modulated decoupling. Very confusing because artists are talking about TPPI, and that has to do with how you add up transients when you're phase cycling, to get rid of artifacts. There's nothing to do with that, nothing at all. It's just a similar atom, very. So, this is a paper from Griffin's group, and they're all 95. So the knowledge that CW isn't the best that's out there, we're pretty confident about that, and it's converging so slowly. And the intuition is that if you could make the cycle time seem faster, even though we're not allowed to turn it up and just make the CW be twice as strong, but could we do something within each 2 pi pulse? So that there's sort of a shorter cycle time within the one Rabi precession period. would that help in some way? You know, have a shorter pulse element inside of each teapot. Two pulse phase modulator. So what is it? Continuous, windowless, so this is for putting it on the proton channel while you're going to detect carbon. Irradiation of the protons, shorter RF element than the G5 cycle. You're going to repeat this element that has two pulses. Two pulses have roughly equal flip angle. So each of the pulses is a pi pulse. What's the difference between the two pulses? Well, which is the phase. How different is the phase? That's the weird thing. It depends. And it's empirical. And you set it up on your sample at that field, you know, all the details. If you change the temperature, you might have to reset. So the phase difference could be quite small or up to 50 degrees. The flip angle isn't always exactly pi, and this is empirical. Now, the fact that it's empirical, yeah, it's not perfect. So this is a cartoon. So actually, this is already super cycle or no? -5. Element seems to show two of them back to back. So I'm wondering if this is already intended to mean something super cycle, then I picked it on graphic. Okay. This is out of a different review article, more recent, Vladimir Vladimirovsky and American Works of the MRF, which has a broader range of topics than just how to decouple your protons, but it begins with some reflections on the history of decoupling protons. Now, and the performance dependent on alpha and delta phi, especially at high MAS, they are optimized empirically. And that leads to a practical issue, which is that if you have RF instability, that means that the room temperature is changing, so your amplifier of your pulses is changing and its amplification. Did you know that the temperature is very, very important feature to the instrument, especially about the pulse count? Or if you have inhomogeneity, which means that if you look inside your sample, you come closer to a turn of a coil, you'll have more RF. If you come further away from the coil, like maybe the center of the sample, that might be the best shim spot, but it might be a weaker RF. So you have spatial inhomogeneity in your RF, you have temporal instability because of the room temperature and other things. And as that happens, your decoupling is like getting better and worse. But look at this difference for some cases, like I think this is a general pair of protons. And that's beautiful right there. It's kind of improvement and with a comparable RF in that case. One of the things I thought I had in the slide deck and I didn't see it, and I just want to say it, it's a little bit out of order. When we were sure that CW was not the best sequence, one of the tells, you know, was that it just gets better so slowly, but increasing the power. But also, if you're doing CW decoupling, you should be aware that even up to pretty high powers, even up to like 9 kilohertz, exactly where your transmitter is can be a quite big deal. Like, are you right on the general pair of the CH2, or did you somehow by mistake move over to the water or over to the metal? You should look at your spectrum, you can see it's not the same. As you move your carrier around with CW, you also have some change in performance. And you also have some change in performance with instability and inhomogeneity. Is this even less stable? Yeah. But just keep in mind, we had these issues already with the CW, and that's part of how we knew we needed a better sequence. So some other pulse sequences that are in the family came out later on from different labs around the world, and they perform maybe a little better here or there, but they're sort of in the same range. It's not just that you're going to resolve your peaks better, But as you are resolving them, you are also improving your signal to noise, and we're desperate for that. So this was a big deal to have this family. Do we completely understand what the average what happened to that second order term? I mean, I didn't tell you today, and I don't think it's all there. I looked at it, there's some analysis, there's some tediousness to it, and I just didn't feel like there was a gem of an insight there that I could convey to you. So this is better in part because it's a shorter element. And in some way that is not crystal clear to me, it is helping with those second order pieces. In the very high frequency spinning limit, this idea that we're going to have RF that will be more than twice the rotor period stops spinning. Okay, I'm talking about like fast spinning. We have a rotor here, actually two of them that go to 60 kilohertz. People around the world have rotors that work nicely up to 160. So even just our 60, yeah, we cannot irradiate at well over 120. Which is what the requirement is. It would need to be like 150 to 180, but we get that day in, day out. So what can we do? We don't want omega 1 to be comparable to omega R. So the other possibility is that omega 1 is kind of weak. It's way down below. How well does that work? Now, I think it would work really well if you could get omega R all the way up to 300 kilohertz. People are working very hard on that. But given the rotors we have, 60, 111, these are commonly used rotors. 60 is the 1.2 or 1.3 millimeter OD. 111 is an 0.7 millimeter OD. But the cool thing about it is you get so little material, less than a kilometer. And you get a reasonable spectrum, and in many ways it's better resolved. Not much material in there. Other challenges, there are definitely other challenges, we can talk more about that, but anyway, we're making, the field is making a lot of headway towards this target of being up around 300, 500 kilohertz, but you're not gonna be using RF that's 3 times higher than that, I don't think, it's not today. So you're gonna use a dipole decoupling RF that'll be weaker than omega R. And that's okay because the dipole coupling is much weaker than omega R. So it's mainly provoked by the spinning, which is sort of that picture from Matthias Herd's paper and his thesis. It's like now we think about it the other way around. We say MAS is doing most of the work. And if there's a little bit left over because of second order terms, that's what lives on the RF. So maybe you could use liquid-like decoupling sequences and assume that all you have left is J. Doesn't seem like that's going to be quite right because of what we said about second order terms, but it's a way to start. So you could have just high pulses or maybe that famous decoupling sequence from solution NMR. Okay, but actually a really nice paper came out yesterday.
Where are the other ones? In order to actually get it.
And would that even cover your spectroscopy? Yeah, that's a good question. So if I'm spinning at 60 kilohertz and I say my omega 1 is weak, what am I saying? 10 kilohertz, 15 kilohertz? And carbon, what is my spectral width? So those pulses at the face of it are not going to cover my carbon. That's the carbon. Actually, we've been talking about proton decoupling, so we need to cover the proton spectrum. And let's say we were on a 900 and we want to cover 20 ppm. That's almost 20 volts. We cover. So yes. So similar kind of thinking comes up where it's not going to be CW, but you're going to have shorter pulse elements inside. Like if you think about the RF string, in the time it would have taken you to do a full cycle of 2 pi, you're going to have a whole bunch of little pieces in there, and hope that that somehow gives you the bandwidth that you need and the performance that you need without that much power. So one of the first examples of this that came out was from Van Meyer's group around 02. And it's called XIX, where the I stands for inversion, and so it's sort of like X things far, like a two pulse X things far. Windowless irradiation, a repeat of two pulses of equal width, phase shifted by 20 X far. But I think there was already something about this. Insensitive to flip angle of the individual pulses. So it doesn't really have to be a high pulse or anything. Sensitive to the pulse width only in terms of how many units of rotor period you have. Relatively easy to implement now. So that's a lot of virtue. And so it is working in a different regime. So these two pulse sequences that I'm mentioning are, I think, impactful day in, day out. Look at the papers from solid state NMR, look at the pulse sequences we have installed here. You're going to see this acronym. So at least I'm giving you a basic level description of what the pulse sequence is, what its properties are, and why it was needed. But I didn't really give you the average time treatment of it because I don't think it's you're not going to get something elegant close form out of it. So if one of you is actually interested in this, like for your paper or for something you're doing, we can certainly talk about it. Now, other developments. So numerical, non-physics based optimization of phase modulation. So I just put these out like some smart person just did this and here's YouTube. I didn't say how they came up with the idea. I didn't say how it's treated theoretically. Here's one where the PIs explicitly said, we didn't use it right at all. Well, we did this, and this is not recent. So this was early. This was early to come up with an idea like this. Lived in our council's group. I'm just going to have a pulse where I change the phase really often, and I'm going to ask my computer program to make random guesses like a Monte Carlo simulation. You all know what I mean by Monte Carlo simulation. You just make a guess, and if it's a bad guess, you make another guess. If it's a good guess, you stay in there for a while. And I'm just going to do some things with the phases and see how it performs. And if it's bad, we'll just try again. We'll just leave this computer program running. So it's a simulation that's good enough. It's a good enough simulation that I'm going to find for the pulse sequence that really narrows it. I have no idea how it looks up here. Different, but somehow related ideas to use optimal control theory. Many people have contributed in the solid state right now. Urban Reach group, Niels Nielsen, and Tossner and his group. These ideas came originally out of, I think, efforts from Senator Laser, which focused a little bit more closely on solution. But there were many collaborations involving all those players. Earlier papers specifically on decoupling, Dave Corey and Kitagawa, separately. I have the name of a program, not a person here, because it has a module on optimal control theory that's we can look into. So I can't point to the one pulse sequence that decouples protons better that came out of optimal control theory, but I think people hold out a lot of and there have been some interesting developments there. And are we expecting more from AI? Absolutely. I mentioned another very recent review article that also covers solid state decoupling. I think if you want to read more about it, that's the third review article that I think might be helpful. And I think that's it. That's where I stopped. So just give you an idea what people have been doing for decoupling, why it's harder than just getting rid of decoupling as a solution, and what some of the things people are thinking about. So that I know I've said this before, that might be it for solids lectures for this year. If not, I don't know. Rather than a solution cancellation, I'll and what I was going to suggest right now, it's 2:15, and we can take a little break, and we have the room until 3:30. And I was going to suggest that we stay, if everybody could please stay, including you, Fortunatus. And Masha, if you're writing a paper, we just kind of do a go around talking about the topic you picked and any problems you're having, digging in on it. Okay? Does that sound okay? So can we take 5? Right now it's almost 15 after, so we'll reconvene at like 20 after. Sound good? Okay, so before we stop, is there a question on decoupling before I? No? Okay. Good.
But your first. When is this speed? I have to look at this. I didn't. You were so, I didn't need to be a split. And I had to swim by feeling. Oh, okay. So I, now so this is a wall. I didn't know this kid. And then, you know, like. Pretty short. Yeah, so I was just thinking of some. Oh, yeah, that's what I actually. Oh. See. That's. Nice to get like. You don't. You have to. You have to do it. And then yes, so like will be asked questions and then you are the reader, right? And questions are respected in the project.
Yeah.
When someone asks you, you know, like, how does this kind of posting work for the kind of work one that you spend on? Like that's they could ask it. You don't think about assumption. That's the thing. So what's the important? No,
So Fortunatus, did you want to talk with us about your paper?
Yeah, I was looking at what to do for the final project on the paper. Then my interest is that because I've been working on generating some NMR data, but I find it difficult for, I mean, even though I'm still optimizing the process, but I have some raw data. So I'm thinking of the topic that will help me to perform some structural calculations. So based on that, I was able to have some paper that I would suggest so that you can guide me to choose the most appropriate one that would be of benefit, not only for the lecture, but that's something I can also learn from in order to generate structure from my experimental data. So
We're having trouble hearing. I heard something about genetics. Can you slowly say it again? It might be something with our speaker or with your microphone, but just try again a little slower.
Okay. I said I am currently working on generating some experimental NMR data. So based on that, I want to choose a topic for this course that revolves around structure calculation from the NMR data. So I've been able to, and then my supervisor said that I have to use explore NMR in order to calculate the structure from the data that I have. So based on that, I'm proposing a topic that has to do with a determination of NMR structure from the chemical data. So I have a paper from the title is Using Explore NIH NMR Molecular Structure Determination. That is one. It is written by in 2026 by Sweetheart and others.
Okay, so let me just repeat back. Your topic will be about Charles Schroeder's work on Explore NIH for structure calculations based on NMR constraints.
Yeah.
Seems like a good topic.
Yeah, I have the paper. Then I have another paper here also that says protein structure determination from NMR chemical sheet.
I had like one lecture on structure calculations.
Yeah.
Maybe tomorrow section. You didn't have it
So
yet.
I don't know if this would be nice to work on for the final project.
Did you say that again, please?
I was wondering if what I have or if what I'm proposing is good enough for this exam.
I think it's a good topic. Yeah, that's my opinion. Yeah. Do you have any questions about the subject? And perhaps you could also consider to bring them to class tomorrow. But do you have any questions right now?
Okay, so do you mind if I send the papers so that you can take a look at them before I start working on them to have the final presentation that
We
I
don't
want?
mind at all. No, we don't mind at all.
Okay.
That's fine.
O-
Okay,
Okay, so
thank you.
so I should go with this, right?
Sure. And you can send
Okay.
the paper to myself and to Art. That's good.
Okay, so is it? I will send the paper as it is, and then I will. What is the report? The report? How is it going to be? Is it like presentation or to make a report from what I understood from the paper?
You are writing a paper. You are writing
Okay.
a paper. I don't know if you guys got from Art any like recommended. Yeah, I don't think he's I'll say all the length. I think in past years, it's been, 5 to 10 pages and that kind of length.
Okay. It's like
There's
a review of.
there's no expectation that you're coming up with, incredibly creative novel ideas. You might just summarize a subfield that interests you that you didn't really hear that much about in the class.
Okay.
And there's no instruction that you must stay away from your own project. If you think you really need to know everything there is to know about TOR, you can watch your paper on TOR. We didn't say you have to stay away from the PhD. Or you can just make something that you think is a funny talk. Just or something fun. You can
Okay. Like, what is the format of the paper? Is it like review, or I should summarize what I understood from the paper?
What's the difference between those two? What's the distinction?
Okay. Okay. Thank you.
Could be both of those things are true, right? I mean, I rather think that you're looking at a subfield rather than a single paper, but some single papers really are a subfield. Like if you took the paper describing Simpson or the paper describing spinach, that's a whole subfield. Both of those, they're just amazing. Do they need to be summarized? Do they need to be rewritten? No, but you're just showing us that you really read it and thought about it or something. That's fine. That's fine, maybe.
All right.
So in this explore the monster of a program. If you show us that you really have mastered it and it's free, do you have it on your computer? Or Gina's?
Yeah, I'm here.
Do you have that program on your own computer? Have you installed it?
Yes, I've been able to install the Explore NIH.
Good. Yeah, because when you're reading about a program, it's a little bit more engaging if you actually can open it up and play with the manual.
Yeah,
Good.
it was. Yeah, I've been able to install it, but I don't know how to use it very well. I mean, I don't know how to use it at the moment.
Are you
Hopefully, I'm going
aware that he's done many workshops and some of them might be out there on YouTube? Well, that's another thing to be.
sure. I will.
He's very generous with
I will
teaching. Yeah.
okay. Thank you so much.
Okay, good. All right, anybody else want to go next? People are avoiding eye contact. Yeah, okay.
So, working, I'm looking at something called DNP. Again. So you might really just do the dashboards. Usually start by polarizing. That's because the German should like alarms. But you can also start with an electron. The electron has the gyromagnetic ratio about 600 times out of there. So if you can transfer the electron to like that here, ideally you get a much more of this. But some of the problems with TAP that you have to put it at the very. And as a result, usually in like solid state NMR, you can go with state. You still have some like local after is spinning and allowing the notion of as a result, your CSA is kind of average. But at low temperatures, your CSA becomes infinitely. You kind of exit that fast exchange with each molecule might happen. And so one way people will solve this is there's something multiplexing is just like uniformly labeled all around. And monotoxins is labeled specific clusters. First of all, as a result of that complicated CSA, your spectrum is incredibly very marginal. So you do like what many experts identify. Now I'm just following my instincts, so like a bunch of posts. But like in order to transfer ionization from the electron to the used particles. And when I was just like casually thinking about this, it's like a transfer event. Really can associate some selection rules with experts. I was wondering if you could simulate multiplexing experiments. Like changing or usually we use minimally polarized microwaves. It's like circular microwaves. I don't, it's true. Like I read a paper about circularly polarized microwaves, and it does do something. Well, removing people see a good shoot. Dephasing of liquid first.
So, a lot of what you said before you were going to start speculating was spot on, and also, you might enjoy looking at the different mechanisms a little bit for DNP. And my own personal feeling is, having watched this stuff since, I don't want to say now. The recent work from Thomas Prisner, I think, is pretty not only of practical importance, but conceptually it's just nice. So you might want to look at his recent papers. I don't remember, I'm sorry, I don't remember the name of the student that I know. But he's kind of relating the mechanisms to each other rather than talking about them as if each one is like a uniform. Also, he and others are pushing these mechanisms so that they work in solution. Now, that might not be what you wanted to do with them, but it's a very tall mountain I'm trying to climb it. We'll see the progress. So you might enjoy some of his papers, but if not, if they don't make any sense, you may just look at those review articles from, I don't know, every 5 years from a review article on DNP and about the polarization mechanisms in particular. We've written more about the line running, but I feel like for what you're talking about, it'd be nice for you to dig in on the mechanism. And then the other thing is like, you have to have that electron in there, right? And people have really different approaches as to how they get an electron into their sample. And it's been very creative work, especially from analyzed parts. Yeah, we need some stuff, Rivka in particular in the lab, and I feel like it's something that's worth picking up on and continuing. I don't think we meant to drop it, sets and problems, but what I was gonna say is that Anasage and her collaborators have been very creative and very thoughtful about their interpretations. So you have data from like 300 radicals, how do you make a story out of that? Well, they kind of did. They have an interpretation of what why this one is better and why that one is better. That I think is what creating and they're thinking. Man, they've worked out how different systems they have. Really great collaborators on the synthetic side. So that's another direction you go. You can't do everything, right? Like if you get into the mechanisms, maybe you don't have time for all the radicals, or vice versa. You pick something like that.
National story that they will also working on developing polarizing agents, the right perspective.
Yeah, no, they're definitely not the only people. I just mentioned them because they write some nice review articles and they review so much, but there's okay. You have a question before we go to the next person? I mean, you don't have to ask right now, you can ask us later. You guys might want to know what the deadline is, not know what the answer to that. No directions, no deadline, but write a paper. Okay. Okay, who would like to go?
I guess I had some. I wasn't exactly sure what was wanted from the paper, so I earlier in the class I was reading in your hospital. Spin is goes into like sort of mathematical variations of how spin rises for like some groups and maybe that's super for this paper. I don't know.
That's really what you're passionate about,
Yeah.
learning more about. I think it's
Okay, so that maybe I don't know how I have notes for people. I don't know what the I would probably go into. So I guess they just you're driving this. That's what. Yeah, I'm not really sure.
Yeah, sure, but
But
something like that.
something along those
Interesting,
lines.
it's interesting. So pretty far from biophysics.
Yeah, it's sort of just how like spin arises from the signatures underlying, um, yeah, or the other idea that was too theoretical was to parametric relaxation. Yeah, that was.
This is one of those things you can take it like, pick a topic where you'd say to yourself, when else will I ever learn this? Why not? Why not? Of course, it's good for that. If you're just reading for passion, but staying with it for a few hours rather than just a few minutes. That's fun. I look forward to seeing what you're doing.
So lately I've been kind of working on setting up some phosphorus experiments for nucleic acids and this phosphorus relaxation on the backbone. And there's like a few old papers that I picked out that I haven't gotten through, so I'm ready to report on the literature on what we pulled on what has even what I'm trying to
The literature of phosphorus relaxation resolution, is that what
Yeah.
you mean? Well, one of the things people are always on about is what is the right field to do those measurements at. Another one is how do you get the fundamental fine structure constants you need to fit it, like how sure are you about your rigid CSAs? Percent solids, percent liquids. But it is important that, that you're thoughtful about that, is that something. Or if your model is only involving the isotropic shifts, can you derive those from your data, or do you have to assume some model? Those are two of the things that often come up. What did you encounter on the practical side that's different to doing comparable CDMG you agree?
Yeah.
For let's say Harvard or Ivy, when you encounter it with the phosphorus that you can see before.
Well, like the main problem that we were having is like actually trying to find a system that has worked on because the surgeon is not super great for it.
In order to resolve individual site tuning?
Yeah, so now that we have a sample, this is kind of
So how did you solve that problem?
well, how did I do
Is
this? Oh,
with good surgery?
so my project is about unit base opening,
Mhm.
and so we have another chemical for opening,
Mhm.
which is just adding a deleted lines. This, and so turns out that when you add that, they realize it shifts the sugars into very nice low resolve regions. So like our hypothesis was that okay, let's see green line, this is 4 we're shifting methylated sites in our DNAs, then phosphorus is somewhere there. And they are. So now we can actually.
So this is actually several bonds away from the phosphate, but it's still shifting.
Yeah, the common is 3 bond coupling, so it's really small. So the transfer is not that. But it's just
But does that have an effect on the phosphorus shift, so that shift is a little bit more unique?
yeah,
Do you think that's because the conformation preference changes?
yeah, there's a relationship between the macromolecules and the phosphorus chips. There's this deep one space. Yeah, that's one. Yeah, that's one.
Okay, Krishna, you're the last.
So I haven't narrowed down to one topic. I'm like deeply focused in mind. So initially, I was thinking about writing a paper on like hormone derivation of all these effects or mechanisms in the cause effect.
Oh, what I was just, yes.
During all this fluid Hamiltonian form. And the reason I thought of that is because we have a zero feeding failure, was happy failure in the theory. So I think it is a good device. I have a really good idea of what we learned in the class. So that was one idea. The second idea was while I was talking to other lab members, extracting CSA tensors from the phosphates that are in the lipid rafts to study the dynamics of those phosphates.
So for the first one, I feel like you're trying to recast a problem that's in the literature in a different way. Right? That's pretty big for this. I mean, you might have had a very good idea there, I'm not sure. But I feel like it's half of a piece, it's not a term paper. It might be a very good idea. I had never thought about that. And are you sure that there was already a paper that starts from that point of view? Are you sure?
I mean, most of the papers I have found are review. There is one we did a paper by Lee and the first author, and it goes into some level of details, but we don't see the equations very explicitly yet.
Yeah.
It isn't like a comprehensive explanation of solid spaces and all these concepts from the theory of the
Great. Well, there may be a paper out there that we haven't read and that we should read. But if you're doing this and it hasn't been done before, I just feel like to figure out the kind of paper. Might be incredibly good exercise and even a good contribution to the literature, but maybe too much between now, whatever I'm good about this. Okay. So your second one, I think, allows you to access an existing literature that is pretty bread and butter stuff for solid state NMR. Like what are the CSAs already that we know about for P31? What are the chemical trends? What have we learned from measuring them? What's complicated about it? Or like, is it easy? Is it difficult experimentally? When people fit them, what are the errors based on? Then could you have predicted this based on quantum mechanics, and would you have gotten it right? Or is this phosphate a really difficult case because it usually has counter ion and it's charged and everything? Or are people getting a lot of success there? All this stuff that's like fantastic training and it's within reach. It's kind of normal NMR stuff, but you take the time to learn it. So it feels to me like it would be a very good topic to just, especially since you're going to be measuring some phosphorus, just to master that literature, and then you're not putting yourself up against a kind of super steep challenge and panicking when it's time to turn it in. I don't know, that's my behavior actually. But and you can take it in different directions. You could put a creative piece of it in, but you could also just summarize it. Depending on your time management, so phosphorus, has had practical use instead of chemical shift. The isotropic shift as a pH indicator of physiology, the impact it has on nucleic acid studies. You're of course very aware of like GTP and hydrolysis and enzymology. So a lot of material science. Like there's a lot of applications for chemists, material science, biophysicists. So you'll find a nice book literature. You said 3 ideas.
Yes, the third idea was, uh, I mean, the third idea was like, it seems like a replicate of the literature, which doesn't sound very exciting. It's like the analytical treatment of the cross polarization, going through all the mathematics of CP, cross polarization, and solving it, and like, and it's been done in the literature. So I think that that's just a replication of it.
I mean, if you turned it in, it would be fine, but we did a fair amount of that in class, and then you could just take it, do it another level of detail for sure, things that I skipped or said, maybe for an exercise for the student, or practical aspects, or, other elaborate, yeah, sure. But I don't know if you would learn as much from that. If you turn that in as a paper, I really want that. What we did in class is based on a specific paper with Mark Call. This is the first author from the 90s. And that covers how you get the band selectivity as well as just the CP dynamics. There are lots of older papers online. All the ideas of the proton bath that we were talking about, spin diffusion and the protons, we talked a little bit about today, how that figures in while you're trying to make the CP. And when we talked about CP, we left all that out, all the relaxation. That picture, and that's very important. So there's stuff we didn't cover that you would learn about. So it could be fun, very good topic. But the sooner you just pick between them, so you can just start to read on it, easier. Yeah.
We also didn't talk about various different applications.
There are many. There are many to discuss. Yes.
CP and the legal working.
That we talked about today a little bit, but
Oh, it is.
yeah, but just as a, well, just the condition itself, but not that much about like what people have done, but yes. So yeah, there's a lot you can talk about.
CP or butyrates.
Or
CP structure.
like spectral editing, like how CP behaves if it's a quaternary center versus a CH. It's a lot, there's a lot.
And finally, response to magnet.
So I think either of those could become a very good topic, but just pick one or the other so you can feel frozen. Other questions? So, May 8th is sort of the end of finals week. Columbia. I don't know if it's the very end or.
Yes.
It does say something, I just haven't read it, is that true? Anyway, I was gonna suggest May 8th because that's sort of the end of the finals week. And then we can turn in our grades at reasonable time, make the registrar happy. None of you guys, I don't think, are gonna be affected by exactly what grades turned in. Guys will do it on time if we can, so. Turn in your paper by May 8th, that would be best. Other questions or? Feel free to send it by email and then you'll get arts in, or bring it to class tomorrow, and then you'll get arts in her book. Bye now.